So sorry for the interruption. There is a poor internet connection. So I was trying to explaining that at x 100 meter we can again find a Reynolds number, which is actually greater than the critical Reynolds number, and then we can use the Nusselt number correlation for the turbulent flow at x 100 meter. Just to recap, at x 1 meter, we found the flow to be the laminar flow because the Reynolds number is less than the critical Reynolds number at x 1 meter, and then we use the Nusselt number correlation for the laminar flow. But at x 100 meter, the flow is turbulent, and therefore we have to use the correlation for the turbulent flow. This is my correlation for the turbulent flow, and when I substitute the value, I will get H 12.4 watt meter square Kelvin. So my change of temperature with time will be second. So in this question we are given a step, and we need to find the change of temperature with time. And for this, we calculate the heat transfer coefficient rate at x equals to 1 meter. We found the flow is laminar there, and we use the correlation for the laminar flow, and then we do a similar exercise at x equals 100 meters. And we found the rate of change of temperature with time at both the location. So moving to the different question. So in this question, there is an array of 10 silicon chips, and each of length L 10 mm on the side is insulated on one surface and cooled on the opposite surface. And the cooling is actually done by the air which is flowing at temperature 24 degrees Celsius, and velocity of air is 40 meters per second. When in use, the same electric power is dissipated in each chip, maintaining a uniform heat flux over the entire cooled surface. If the temperature of each chip may not exceed 80 degrees Celsius, what is the maximum allowable power per chip? What is the maximum allowable power if the turbulence promoter is used to trip the boundary layer at the leading edge? Okay, so we need to find the maximum amount of power that the heat transfer that we can ensure from the chip, because we cannot let the chip to be more of so the temperature become more of 80 degrees Celsius, and there is a air flow from the left hand side with a given velocity and temperature temperature values. So first we need to find the heat transfer rate, and for this obviously we need heat transfer coefficient, which we can find from the correlation that we are using in this lecture. So again, to determine whether the flow is laminar or turbulent, we need to find the Reynolds number of the flow. this is my Reynolds number, which is less than a critical Reynolds number for the flat surfaces. So we can assume that, or we can conclude that the flow is in a laminar state. So we can use the laminar Nusselt number correlation to find out the heat transfer coefficient. And on substituting the value, you can directly write the heat transfer coefficient as watt per meter square Kelvin. I can find the heat transfer rate from the Newton's law of cooling. This will be by heat transfer. Now, the question says that what is the maximum allowable power if a turbulence promoter is used to trip the boundary layer? So we are making the flow into the turbulent in nature by introducing some turbulent trip. For example, this is my flat surface and some roughness or kind of a thing. Now, when the flow passes over this roughness, it becomes turbulent in nature. And for this, we can use the correlation, turbulent Nusselt number correlation, to find the heat transfer coefficient, and then we can find the heat transfer rate in this case. So the process is similar. We use now the turbulent correlation Nusselt number, Nusselt number correlation here, which is and we know that in case of the turbulent flow, the Reynolds number is actually varies by 4 to the power 5 or 4 by 5. I mean, the heat transfer rate is actually proportional to the Reynolds number to the power 4 by 5 in the turbulent flow. So we can get the heat transfer coefficient in case of the turbulent flow. Let me write this H3. And similarly, the heat transfer will be so this will be my heat transfer when we make the flow forcefully turbulent in nature, and this heat transfer is way larger than the heat transfer when the flow is laminar state. So here we can conclude that for the turbulent flow there will be the more heat transfer for the same properties and the variables of the flow when compared with the laminar its laminar counterpart. So here in this question we have done the same thing that we are doing since the last 2-3 questions. We found the heat transfer coefficient from the correlation, and even to find out which correlation we required to find the heat transfer coefficient rate, we first identify the flow, whether it is in laminar or in the turbulent regime. Once we get this by finding the Reynolds number of the flow, we can use a suitable correlation. So here we first use the correlation for the laminar flow because the flow we got the Reynolds number which was less than the critical Reynolds number, and we found the flow is in laminar condition, and so we use the laminar correlation to find the heat transfer coefficient H, and then we found the heat transfer. Then we make the flow forcefully as in a turbulent in nature, and we use the turbulent correlation then and to find to form the heat transfer coefficient rate, and then we form the heat transfer. And we conclude that the heat transfer for the turbulent case is much higher when compared to its laminar counterpart. Now let's move to the different question. So here we need to identify the correct statement. So the first statement says that for the case of fluid flow over the flat plate, the transition from laminar to turbulent flow depends on the geometry, surface roughness, stream velocity, surface temperature, and the type of fluid. Among other things, it is best characterized by the Staten number. And so the first statement is not completely true actually. So the transition from the laminar to turbulent depends on the various phenomena like the surface roughness, upstream velocity, the nature of flow, the density of flow, the velocity of flow, could be the surface temperature as well, but it is not actually defined by the Staten number. We are solving many problems in this lecture, and we found that we need to calculate first the Reynolds number in order to distinguish the nature of the flow. So it's the Reynolds number actually, which actually distinguish the flow between whether it is a laminar or turbulent in nature. So the first statement is not completely correct. The transition actually depends on these parameters, but it can be usually defined by the Reynolds number instead of Staten number. So second statement says that the fluid temperature in thermal boundary layer varies from Ts at the surface at about T infinity at the outer boundary layer. The fluid properties also vary with the temperature, thus with the position across the boundary layer to account for the variation of the properties with temperature. The fluid properties are usually evaluated so-called film temperature as Ts plus T infinity. So the second statement says that since we have a flat plate and there is a thermal boundary layer, there is a variation of the temperature from the surface, which is at Ts to the flow, which is at T infinity. So the temperature will be changing from Th to T infinity, and during inside this thermal boundary layer, the properties of the fluid could change, and therefore we define this mean temperature. Therefore we define the properties of the fluid at this mean temperature, because the properties of fluid could change actually could depend on the temperature. So the density or the viscosity of the fluid actually is a function of temperature, and since we have a temperature difference, in the reality the density and the kinematic viscosity or the viscosity or just the dynamic viscosity would change as the temperature changing from the wall to the surface, and therefore it is suitable to define the mean temperature, which can be given as the sum of the temperature at wall or the temperature of the solid wall and the temperature of the flow divided by 2, and we define the properties like the density, viscosity of the fluid at this mean temperature Tf. So the second statement is correct, but not the first statement, so the option is B. So let's go to the last question. So there's the Weather Channel report says that it is a hot, muggy day with a air temperature of 90 degrees Fahrenheit, a 10 mph breeze out of the southwest, and bright sunshine with a insolation of 400 watt per meter square. Consider the wall of metal building over which prevailing wind blows. The length of the wall in the wind direction is 10 meter and the emissivity is 0.93. Assume that all the solar irradiation is absorbed, that the irradiation from the sky is negligible, and then the flow is fully turbulent over the wall. Estimate the average wall temperature. So we need to find out the wall temperature here. So the heat transfer will take place due to the convection as well as the radiation. And we have given the how much heat transfer will be there from the radiation, and we need to find out the temperature of the wall. And the question says to assume the flow as a turbulent in nature. That means if we need to use the Nusselt correlation, we have to use the turbulent Nusselt correlation to find the heat transfer coefficient. So first, write down the energy balance. This will be my energy balance because there is no heat generation and there is no variation of temperature with time. So the variation of temperature is completely steady. So this will be my heat transfer equation coming from this energy balance. So there is a wall. So heat will be out via convection, and there is actually incoming of heat from the solar radiation, which can be defined by this expression alpha, and Gs is some irradiation which is coming from the sun, and Q is my Newton's law of cooling, which shows there is a convection heat transfer, which says that there is some loss of heat from the wall of the building into the air via convection. So it can be written as there is a wall of this building and there is a loss of heat by the convection, which is given by Newton's law of cooling, and there is an incoming of heat due to the solar radiation, which take care by this Stephen Boltzmann law, which governs the heat transfer rate due to the radiation that we will look in upcoming weeks in detail. So this will be my equation, and I need to find the temperature Ts here. First, we need to find the heat transfer coefficient because it is unknown here. So for this, the equation says that to assume the flow in a turbulent in nature, so we will use the turbulent Nusselt number correlation to find the heat transfer coefficient here. So on substituting the value here of Reynolds numbers and Prandtl number, I can find out this heat transfer coefficient HL. So this will be my heat transfer coefficient. And now I need to put this heat transfer coefficient into the above question. So for Srinidhi, who joined now only, so let me recap the question. So the question says that there is a building and there is a heat incoming from the solar radiation to the building, and we need to find the temperature of the wall. So for this, this assumption given in the question that we need to consider the flow past the wall as turbulent in nature. So here the temperature Ts need to be evaluated. So we are given that there is a solar radiation, so there is a incoming heat, and building will also lose some heat, and that is due to the convection, which is given by the Newton's law of cooling. So when we do the energy balance, energy in, energy out, so this energy in is due to the radiation part, and this energy out will be there due to the convection, heat convection. So we identify the equation. So radiation part will be governed by the Stephen Boltzmann's law, and the radiation which is given in the question, and the heat which is going out from the building actually governed by the Newton's law of cooling, because it is in convection mode. So we need to find the temperature Ts here, but here the heat transfer coefficient is not given. So first we need to find the heat transfer coefficient. Now the question says that to assume the flow over this building as turbulent in nature, so we are using the turbulent Nusselt number correlation to found the this heat transfer coefficient. So this is my turbulent correlation to find the heat transfer coefficient. So if I substitute the value of Reynolds numbers and Prandtl number here, I will get the heat transfer coefficient as 12.4 watt meters per Kelvin. And now I just need to substitute this heat transfer coefficient and all the variables here in this question, which is given in the question. So here the irradiation is given as 400 watt per meter square, and this emissivity is given as 0.93. So this is my Stephen Boltzmann constant, and this I need to find out Ts. So I'm solving this quadratic equation, which just has the power of 4. We just can find out the roots, or we can use the trial and error method to find the Ts here. And the Ts will be around 302, which is 29 degrees Celsius. So this will be my temperature of the wall. So again, I can recap the question here. So the question says that there is one building, the solar radiation is coming, and there is some heat which is coming out from the convection, and there is a flow around the building which is turbulent in nature, and we need to find the temperature of the building. So we write down the energy balance equation. We equate, so the energy, incoming energy can be given by the radiation, and the outgoing energy governed by the Newton's law of cooling, which is the heat convection. We equate these to find out temperature Ts. We also found that the heat transfer coefficient is something unknown in this question. So first we use the turbulent correlation to find out the heat transfer coefficient, and then it's just a matter of putting the values into the equation to find out the temperature of the wall. So this is the last question for this week. So if you have any issue, or if you missed something, you can check my YouTube channel. So I will upload this recording to my YouTube, and you can further check. So today we have solved actually question related to the flow past the flat plate surface. In most of the problem, we actually found the heat transfer coefficient by using the correlations, and based on the laminar and turbulent correlation, and then we found the heat transfer. So yeah, that's for today. So we will meet next week at the same time, 3 to 4 on Saturday.